All right. Well, so I'm joined by Professor Dr. Benjamin Zuckerman from UCLA, emeritus, Professor Emeritus. I think was the way you were described on your Wikipedia. How would you describe yourself?
Well, I am both a emeritus professor and a research professor. Fraser, research professor is a title that UCLA likes to give to some of us. So if we're still active doing research and we're applying for research grants or time on telescopes, we can write something down other than
Right.
emeritus, which makes it seem like really old fogies and out of touch.
Right. So it's all of the above. I think obviously the longer you do this job, the more of these titles you get to sort of collect, and then you get to spring them at the whatever whatever is necessary at the time. So for those of you who aren't familiar with your back, with your life's work, what have you specialized in?
Well, I've done a lot of things in my long career in astronomy. I guess it's over 50 years now. And I started out as a radio astronomer back in the 1960s. One of the hottest topics in astronomy was interstellar molecules, organic molecules in space. And this we thought might tell us something about the prevalence of life, the origin of life in the universe. So I started with that in that field, and then went through a number of other incarnations in the subsequent decades. And in recent decades, I've been mainly interested in the study of extrasolar planetary systems in a variety of ways. That's now, just as interstellar molecules was arguably the hottest topic in astronomy back in the 1970s. So extrasolar planets is presumably one, if not the hottest topic in astronomy now.
And one of the things we'll get to the sort of why I brought you onto the show, but sort of in researching your background, one of the pieces of research that you worked on, and I had no idea, was sort of one of my favorite pieces of research that's been done in the last decade or so, and that was the first imaging of an exoplanetary, multi-planetary system. And I'm sure a lot of people, I don't have the picture sort of handy. I'll put a link in the show notes, but people can sort of remember this time lapse animation of this star covered by a coronagraph with multiple planets orbiting around it, and you can literally see the planets going around. So, can you talk a bit about that research and sort of how that all came together?
Sure. So back, let's see, I guess it was
I think it was
I
2011.
guess that paper was published in 2008, but earlier than that, back around 2000 or so, the technique imaging techniques in the infrared had become good enough. So we realized if there were planets out there, massive Jupiter-like planets orbiting around young stars, that we'd be able to detect them. The critical aspect is that this star needs to be young, because when we image these planets, we're not looking at reflected light. Like you look up at the night sky and you see Jupiter or Mars, you're seeing sunlight reflected off these planets. But we're not, the state of the art of astronomy now is not good enough to see quite good enough to see reflected light from planets. So we have to look at young self-luminous planets, which are still hot enough, they're emitting enough infrared energy that we can measure, see them in the infrared. So this was a program that was instituted a couple of decades ago to search for the infrared emission from these young planets. And one of my contributions was to identify young stars near Earth so that we know which stars to target for young planets. At any rate, after a few years of not being successful, we looked at this HR 8799, and amazingly, we saw three massive planets orbiting around it. And then a year or so later, we discovered a fourth one. So there are four planets at least four giant planets orbiting around. I believe it's still the only star about which astronomers, or at which astronomers have measured more than one planet, imaged
Right,
more than one
right.
planet or granted. Now, using other techniques such as the transit technique with the Kepler satellite, other multi-planet exoplanetary systems have been discovered, but HR 8799 still, I believe, is the only one
Right.
that's with multiple planets have been imaged.
It's interesting to sort of to reveal these planets purely by the infrared heat, essentially the light that's coming from the planet itself. The sort of the other technique that I know has been very successful in recent times is the sphere instrument and the espresso instrument attached to the very large telescope, and in that case, they're measuring the polarization of the light bouncing off of the atmosphere as it's coming towards us. So a sort of a similar, I mean, in this case, they are measuring the reflected light, but they're still sort of using a trick. But just the fact that you're not seeing the transit, you're not looking at the side, you're not inferring the existence of the planet, you are directly imaging it. And that's the rest of the planets. I mean, the transit and the radial velocity, they only give you like 1% of the planets out there. It's all the rest that we want to be able to see. So do you see us moving into that regime of direct imaging?
Yes, although it's not clear, at least to me, when this is going to happen. I think when 30, 40 meter class telescopes are built in the next and go into operation next decade or so, that I think the claim is that with such large ground-based telescopes, it will be possible to perhaps actually image in planets in, say, optically, so you can see reflected light or whatnot. I mean, I'm not sure how it's actually going to come out.
Yeah.
Certainly, the best way to go is to go into space, but we're not doing that very quickly. There have been a number of different space telescopes have been suggested, not only for imaging Jupiter-like planets, but even Earth-like planets. But these haven't gone anywhere because I think the world has got so many problems trying to deal with right now that these fun and exciting things just aren't happening because the money's not being spent.
Yeah, I mean obviously there's James Webb, which absolutely is going to launch in October 31st, 2021 for sure.
Right.
And as you mentioned, there's the 30-meter telescope, there's the Giant Magellan telescope, there's the 39-meter extremely large telescope. Like there are some big telescopes coming, but it's that next generation, the like the HabEx, the LUVOIR, these space giant observatories that will take the direct imaging to the next level. But it's
Fraser, you're probably more aware of these things than I am because at my age, I don't expect to see those telescopes in operation. So
yeah, I think we're looking at like 2035 for if the decadal survey actually approves them, then we could see them in the mid 2030s. Even I'll be probably looking for retirement by the time this starts to happen. So I want to talk a bit about some of the papers that you recently published, because I feel like they are just absolutely sort of the Venn diagram of my audience. So the first one that I thought was great and really kind of matched my thinking on this matter was your opinion, based on Oumuamua, the sort of, the recent, obviously, Avi Loeb is saying that Oumuamua is a potential spacecraft probe sent to us from another civilization. And you wrote a paper that I thought made a really compelling case that as telescopes get bigger, alien astronomers won't need to send a probe. They'll learn everything they need to from their own home system, thanks to a big telescope. So can you elaborate on sort of the thinking on that process?
Okay, sure. Well, I've been a fan of the giant space telescopes for a number of reasons for quite a few years now. I wrote a paper a couple of decades ago about using them to guide space probes to other stars and to expedite projects such as directed Panspermia, where we try and send microorganisms to exoplanets and start life on some that don't have life. So I've been interested in this for a couple of decades. More about back around those times also, I wrote a paper where I argued that the existence of these giant space telescopes is actually a strong argument against the prospects for local SETI. That is that for reasons that I won't go into today, but the mere existence of giant space telescopes that the extraterrestrials will have will make it much less likely that any local search for extraterrestrial intelligence will be successful. But most recently, in terms of this Oumuamua object, the first interstellar visitor from interstellar space to our solar system, here's an outline, the argument that I wrote and was published in this paper recently, that if Oumuamua is a spacecraft spaceship sent by some alien civilization, it really didn't do anything interesting at all in our solar system. At most, if it had say a 10-meter telescope attached to it, it might have taken some pictures of the Earth as it zoomed by at us over a period of a couple of months at a distance no closer than 0.2 of an astronomical unit. So limited to what it could do both in time and in proximity to the Earth. And the thing I pointed out in my paper is that this spacecraft took an absolute minimum of 50,000 years to get here at the velocity, its measured velocity. If it came from the very closest star, if it came from anything further away, it'd take hundreds of thousands of years. Well, any technological civilization that's that much time to develop technology is going to have giant space telescopes out in space. I mean, not these, little James Webb kind of things, but things that might be a kilometer in size, for example, rather than 10 meters in size, or whatever. And a whole array of them, an interferometric array of them. So giant telescopes and an interferometric array. And so I just worked out in this paper that if you have such a system of telescopes if the extraterrestrials have such a system of telescopes in their interplanetary space, then they can study our solar system with far more precision over far longer periods of time than Oumuamua could as it zipped by in a period of a few months. So it would make absolutely zero sense for any extraterrestrials to want to send a spacecraft of that sort when they've studied our planetary system to death with over eons of time. During the time this 100,000 years has taken the spacecraft to get here, they're studying with their giant space telescopes for 100,000 years. They're studying our planetary system, and they know far, far more about it than Oumuamua could possibly learn in the time it goes by. So I sort of concluded one of my conclusions was the only probe that would make any sense for them to send, given the capabilities of their giant telescopes, is one that was not a flyby, but actually went into close orbit around the Earth, just like we put our spacecraft in close orbit around the planets of our solar system. They send something, it goes in close orbit around the Earth, and it sits there for months or years or something like that, looking at us up close and personal. But that's not what Oumuamua was at all.
Right. And so when you just do the math and look at how close it got at its closest point to any of the planets in the habitable zone of the sun, Venus, Earth, and Mars, you could match that capability with an array of kilometer size.
You far surpass that capability.
Right. So I would love to.
By the way, with these space telescopes, they already have known that Mars and Venus are not interesting places.
Right.
They're not living worlds. They either don't have atmospheres or they have too much atmosphere. There's no evidence for anything. We know enough about our own solar system and about extrasolar planetary systems now to know that the only really conceivable interesting thing in our solar system, any other creatures that might be out there, is Earth. And they just obviously didn't do a very good job of studying Earth with this.
So tell me about the capabilities of a multi-kilometer sized interferometer. I mean, it sounds mind-bending, but also when I think about the future of us building, assembling space-based structures, it doesn't seem that far into the future that we could build such a thing. I mean, it's a little bit of aluminum and some shiny foil and a camera or two. So what could an interferometer of that kind of capacity, what would that allow us to see about on other worlds around other stars?
Yeah, well, I agree with you that I think technologically, for a technological civilization, not much in advance of our own. And by that I mean, cosmically speaking, say a few hundred years, 1,000 years, building these giant space interferometers is not going to be hard. After all, here on Earth, we have this incredible interferometer that measured gravitational waves passing. Right. I mean, that just seems so much harder to me than building some of these space interferometers. We've already done that. So once you have these giant telescopes in space, you can use them for a whole variety of projects. The ones I'm most interested in are projects that are related to life in the universe. Suppose we discover that there is a living world, that is a world with life on it, orbiting around some nearby star. I'm not talking about technological life, just life of any sort. Then what we can do with these space telescopes is we can study the system as a function of time. We can measure the spectrum of the planet, and in case of our own planet, if somebody was measuring it, they'd see their continents and oceans. They can measure the spectrum of the vegetation, or photosynthetic vegetation. We can see annual changes, our yearly cycles, or long-term changes due to ice ages and things like that. Again, any star that has a technological civilization in orbit around it that's near our solar system now, it's been near us for 1 million years or so.
Yeah.
So they got plenty of time to study. So, even though it seems to us like the ice age is, in the curve, 10,000 years or something, when you can study a system for 1 million years, 10,000 years doesn't seem very long. So they can study us in so many different ways, spectroscopically and time series and whatnot. So that's what's of most interest to me personally, but a lot of my colleagues who study the far edges of the universe could use these kinds of telescopes to study cosmology in ways that are, way beyond what we can do now.
But we think about this idea that right now, even the best telescopes that we have access to, and even that next generation ones that are coming out, they're going to give us 1 pixel. Like one very interesting pixel, but still 1 pixel. Does something that is that kind of scale start to...
you'll be able to resolve that. I mean, as I meant to imply, when you have these giant telescopes, you'll be able to have many pixels on the Earth, and you'll be able to, for example, if somebody was looking at Earth from one of the nearby stars with one of these giant space interferometers, they'd be able to clearly distinguish the continents from the oceans and whatnot. And I mean, depending on exactly, what the resolution is, who knows whether they'll be able to resolve, 100 kilometers or 10 kilometers or whatever. But that's just a detail. But certainly they'll be able to see their continents and oceans and whatnot, and measure the spectrum of the different parts of the Earth, the ice caps and whatnot. Yeah.
And I know that when people, there have been various attempts to send messages out to other civilizations, and people are concerned that if we send out that message to an alien civilization, then the invasion fleet won't be more than a few years out. But obviously, just our very existence and interaction with our planet, our cities at night, the pollution that we're putting into the atmosphere, the fact that algae has been filling our atmosphere with oxygen for 500 million years, like the jig is up. They know we're here. They know everything about us from their comfy homes.
I agree totally with what you just said. Also, I think it's ridiculous to think that there are going to be any kind of invasions for so many reasons. I mean, we are still a controlled by our Darwinian instincts and whatnot. Any species that learns to live sustainably, they've gotten beyond that, and they're not going to be going out and making war on some other creatures orbiting around some other star. Also, their biochemistry is going to be different than ours, so they're not even being able to. I mean, it's going to be just so different.
Right. Yeah. Earth would suck for them, and their planet will suck for us, and so we've already found the best planet in the universe for us.
Right. I mean, we will. I think if there is life, I'm not talking about technological, just life in general. If there is life on planets orbiting around other stars, we're going to find it extremely interesting to study that life, and vice versa. If somebody wanted to kind of study Earth life, which, by the way, they could have done for, as you pointed out, for 1 billion years before we ever appeared here, then that will be of interest, but it's not going to be this conquest or kind of thing at all. It'll be much more just scientific and, gee, we're interested in your biology or something like that. But
right.
We're not going to try and do any harm to you. I think the idea that we have anything to worry about from a technological species orbit that's originated around on some other star, it's just frankly ridiculous in my
right point. Or they would already have been here, and
well, yeah, right, and the fact that by the way, the fact they haven't already been here, or there's no evidence for that, is a good reason to think they're not very common in our galaxy. There must be few and far between, or there's a good chance that somebody would have come here. Now, somebody says, well, maybe they are us, but since all biochemistry on the Earth is basically the same, if they are us, they came, 3.8 billion years ago, and they seeded Earth in some way, and then they've left us alone ever since then. It's right. Not like somebody came like 700 million years ago and introduced a new kind of, or different kind of life, because all life that we've ever measured or studied has got the same basic bio.
Everything is related with a common ancestor. So now you have also done some interesting thinking about what it might take for us to move out into the cosmos and to explore other worlds, to send our own Oumuamuas out to other star systems. And it's not as energy intense as we maybe have been led to believe. Right,
Fraser. My UCLA faculty colleague, Brad Hansen, and I sort of just, had a eureka moment last year sometime and realized this. And we just wrote a paper, which just was published in the Astronomical Journal just within the last month or so. And what we realized, which to my amazement, I've been in this business, actually, before I tell you about the paper Brad and I wrote, I've been in this business actually since the 1960s. I was a graduate student at Harvard, and during the same years that Carl Sagan was a assistant professor there, and my office was right down the hall from his, and we had a number of interesting conversations that late after everybody else went home, or maybe on the weekend, we'd both be there and wander down to his office, and we'd chat about these things. So I've been involved in this since the 1960s in one way or another. And actually, Carl encouraged my colleague and friend Patrick Palmer and me to go out and try a radio search for signals from other civilizations. We did that during the 1970s. At any rate, so I've been thinking about this these kind of problems for a long time. I was surprised that when Brad and I realized last year that it's not necessarily as hard to go, but to take a spaceship between two stars as we all have been led to believe. I mean, the standard argument as to why interstellar space travel is so difficult is because the stars are about a parsec or a few light years apart on average. And unless you get up to very rapid velocities, it's very hard to go that distance, given that separation. But what Brad and I realized in this paper we just published is if you're patient, you wait a few 100 million years, which sounds like a lot of time to us now, but when the Earth is going to be habitable for a couple of billion years more, so a few 100 million years, not that long, you wait a couple of 100 million years, and some star is going to pass 100 times closer to the Earth than the typical star in the solar vicinity is now. So rather than having to go, say, a parsec or a few light years, you only have to go 100th of a light year or something like that. And then if you work it out, that means you could travel with velocities not much faster than the velocities which Voyager, for example, the spacecraft, are leaving our planetary system, our solar system, for a period of a human lifetime, like 100 years, and you could get to one of these stars as fast really near the Earth. So if you want to make a jump to another star, and I'll tell you a reason why you might want to make that in just a second, if you're patient, it's not so hard as people have led themselves to believe. And the reason why you might want to make such a jump is that I wrote a paper back in 1985, so I guess 36 years ago or so now, where I argue that stellar evolution is going to force, or will probably force, long-life technological civilizations to leave their own home star and to go to another star. Now, if there are a lot of technological civilizations in the galaxy, then some of them have already have had to face the fate of their star evolving first to a red giant and then a white dwarf.
Right.
So if this is not hypothetical, if there are a lot of technological civilizations in the galaxy, some of them have certainly already had to face this problem, this conundrum. And so one possibility is to leave and go off to another star system. And again, if you're patient and you wait till one passes by close by, like a long-lived M-type star, something low-mass star, you could transition relatively easily, and then you'd have a home that would last for hundreds of billions of years,
right,
if not a billion years for the lowest ones.
And so,
I
was going to say that's like when we sort of make the case, and this you all the way back to even Enrico Fermi, who had done the math, sort of did the math in his head and said, like, if you send one spacecraft to a planet, and then it has a factory and it makes a bunch more spacecraft, and they go to two other star systems, you could effectively explore the entire Milky Way over the course of 10 million years. 1 million years, if you're going to go 10% the speed of light, maybe if you're going to go slower, it'll take you a little longer. But I wonder if you sort of take into account these close flybys of stars, I mean, if it's once every 100 million years, but maybe you get a flyby that's more approachable every million years. Like it's a numbers game.
Sure, that's right. I mean, it just depends on how close one thing. But these close flybys will make it easier to do what you're just suggesting, Fraser. As long as you've got some patience, maybe for 10 million years rather than 100 million years, somebody's going to come much closer than a parsec, and that'll make a jump easier and will make this so-called Fermi paradox yet more of a paradox.
Right. And so I wonder then, like, did you calculate, like, if you wanted to still do that pathway where you just go to every star system geometrically, but you also take into account all these nice close flybys, does that significantly impact the time? It feels like it impacts your first trip, but after a while it all starts to smooth out into the larger distribution.
It's a good question, and one we purposely did not try and address in our paper. We absolutely, it was a minimal conditions for and minimal transfers. We just let each technological civilization transfer to one or at most a couple of stars, and we did not explore the question you are asking: is, you know, how long would it take, when you factor in this close passage idea, how long would it take to fill up the galaxy with technology? And we purposely did not do that calculation. It'd be definitely a worthwhile calculation.
In fact, sort of while I'm sort of doing the math kind of roughly in my head, if you've got 100 billion stars that you're going to visit, and you're going to wait for some percentage that are going to have, you know, each one has to wait 1 in 10 million times, it probably won't change your flight time, your overall course at all, because you're going to be getting this doubling across, you know, every year that goes by, you're going to have.
If say it's relatively easy to make a transfer in 100 million years, and so you double every 100 million years in the space of, say, 2 or 3 billion years. You've got 2 to the power 20 or 30. I can't work it out in my head, but that's a big number.
Yeah.
So it really depends on how often you decide to make these transfers, I think, as to how much these kind of considerations will impact the ease of filling the galaxy with spacecraft. But you know, factor of 2 taken to a big enough power is going to be a big number. And again, 100 million years is still short compared to the billions of years that particularly the earliest technological civilizations in our galaxy, assuming that there are other technological civilizations, might have arisen. So they might have had billions of years head start on us easily, because Anyway, the galaxy is more than 10 billion years old, and the Earth is only 4.5 billion years old. So if there are a fair number of technological civilizations, some of them had many billions of years head start on us. And if you're transferring every 100 million years, that gives you a lot of possible doubling time.
Yeah, it's interesting. And so like once again, it's made the Fermi Paradox even more troubling, that you don't even have to come up with really advanced, incredible.
Right, you don't have to be traveling at 1/10 the speed of light.
You just have to jump from island to island.
That's right. As I said, you could go at a few times what Oumuamua is traveling at, or what our Voyager spacecrafts are traveling as they leave the solar system, just a few times. And you could do that easily, I think, with something like fission power. You don't need any of these exotic mechanisms to travel a few times faster than Voyagers are traveling, and use the gravity of the giant planets to help you accelerate and whatnot, and then just sort of one sort of human lifetime. There's nothing sacred about a human lifetime. I suspect that in the future, even if we're still made of sort of flesh and blood and carbon, and our descendants are made of carbon and water and all that, the lifespans will be longer than they are now, and then we may invent or develop another kind of life, whether it be something more artificial intelligence and based on some other materials that might be able to live or last a lot longer than 100 years.
It's interesting. And so, the last piece of research that I wanted to talk with you about was your thinking on Dyson spheres.
So in terms of Dyson spheres, I had another eureka moment or I think it was earlier this year, towards the last year. So I mentioned that if you're on a technological civilization that's orbiting around a star that's evolving first to a red giant and a white dwarf, one possibility is to just leave. Everybody leaves. And again, if everybody's leaving, then you really would like to just have a relatively short jump to the nearest star. That's why I think these kind of considerations that Brad Hansen and I wrote about are important if you want to just send not just a probe or two, but send everybody out to another star system. But the other possibility is not everybody leaves, and plenty of the creatures, whatever the creatures might be, stay behind. And they first move outward away from their stars that evolves into a red giant, and then move in towards the white dwarf that the red giant evolves into. And they nestle in close to the white dwarf. Well, once you've gone through all those kind of changes, whatever you are, you're basically living in giant space colonies. It's just no way to keep living on planetary surfaces when you go through such a sequence of events. You can envision our own planetary system where once Earth becomes uninhabitable billions of years from now, we're not going to be living in Jupiter or on Saturn or anything like that. These are just big gas bags. So basically, just about everybody is going to be living in giant space colonies. And once you've got a bunch of creatures orbiting around the white dwarf, and the stars, almost all stars evolve to. Once you've got them living in these giant space colonies, you basically have a Dyson sphere or a ring or something like that. And not only you have the colonies, you probably have big energy collection devices that can collect energy from the star and beam it to the colonies. And then you probably also have giant space telescopes, which you're using to either do great astronomy or maybe to communicate with other technological civilizations somewhere else in the galaxy. So you have all these giant things, giant space colonies, giant energy collectors, giant telescopes. They're all absorbing light from the white dwarf and radiating in the infrared. And you basically have a Dyson sphere. There's just no way to avoid it.
Right.
If you're living around a white dwarf, you are in a Dyson sphere.
Right.
And so the paper I just submitted a week or two ago, the journal basically actually describes how Dyson spheres around white dwarfs have already been searched for, although people didn't realize they were doing that. And also Dyson spheres around main sequence stars, stars like the sun, have also been searched for, and people didn't realize they were doing that. And so this paper described both the searches around white dwarfs and main sequence stars that have already been carried out, you say, without success so far, and they're not very sensitive, so you can't put a very stringent upper limit on the number of technological civilizations that exist in the galaxy from existing observations, but you can put the first quantitative limit on the number of technological civilizations in our galaxy by saying there is no evidence for Dyson spheres around either white dwarfs or main sequence stars. And this enables you to put some kind of a limit on what's called capital N, the number of technological.
And so the signature, this is like looking for an infrared signature of a Dyson sphere. We'll give off a very clear.
Right. What happens
signature.
to Dyson spheres is the space colonies or the constructs, any other construct, whatever construct, absorbs the optical and ultraviolet light from the central star, whether it be a white dwarf or a main sequence star, and radiates it in the infrared, typically at wavelengths of a few microns to about 10 microns. The Earth is radiating mostly at 10 microns wavelength, but we could build, for example, energy collection devices that could be quite happy at higher temperatures, maybe up to 1,000 degrees, in which case their waste heat energy would come out at a few microns wavelength rather than 10 microns wavelength. So that's the range of infrared wavelengths that one wants to search for these Dyson spheres, anywhere between a few microns and 10 microns wavelength. And
there's no natural process that could give you a point source of infrared radiation that's in that.
Well, there are actually a lot. Unfortunately, that's one of the problems here. There are actually quite a few sources that are a number of them that can produce this kind of energy, and you've got to get rid of them or figure out that what's going on. So in the case of the white dwarf stars, for example, many white dwarfs have dust particles in orbiting around them, and these dust particles absorb the radiation from the white dwarf and radiate it, the optical radiation from white dwarf, ultraviolet, and radiated infrared wavelengths. In fact, my colleague Eric Beck and I were the first back in 1987 to discover a dust ring around a white dwarf. And now many dust rings are known. And so if you see infrared radiation from the phones ringing here, it's probably a robocall. I'm sure it is. Yeah, it's a spam call. Anyway, so if there's infrared radiation from, I don't know how to shut this thing up. Sorry. If there's
call for potential spam.
Yeah, exactly. If there's infrared, I get 10 times as many robocalls. I get real calls.
Yeah.
If there's infrared radiation coming from a white dwarf, and we know many such white dwarfs, the chances are it's coming from orbiting dust particles. There's also a chance it's coming from so-called brown dwarfs, which are objects that are sort of intermediate between stars and planets that your listeners probably know about. They also are strong sources of infrared radiation. But in the case of, for example, white dwarfs and also main sequence stars, it's much more likely that the infrared radiation is coming from dust particles than from brown dwarfs. Anyway, those are sort of background sources you got to get rid of. And you got to say, oh, well, it's definitely not a brown dwarf. It's definitely not dust particles. Well, maybe it's a Dyson sphere. But these are kind of issues you need to deal with.
And people, I mean, I've provided sort of the same explanation about this, that one of the most interesting ways to just search for alien civilization. I mean, I always talk about the fact that we have already begun our Dyson sphere with our various spacecraft, satellites, space telescopes, things that are harvesting solar power and doing things is essentially, that's how you get a Dyson sphere, is you just do it bit by bit, and after a while you realize you've enclosed your entire star and you're harnessing every little piece of its radiation. And then of course you have to give off that waste heat. And people always make this, they always say, well, couldn't super smart aliens be able to hide the heat? Couldn't they use the heat? Well, like, how do you respond to that? Sort of like, if we think
the only idea I've ever heard of is that you keep using it, so you degrade it, you keep transferring it in some way, maybe from a hotter object to a cooler one, so eventually it comes out at such a long wavelength that you really wouldn't be sensitive or notice it or be looking for it. So there's no real reason to do anything that extreme. I think there's really no way to hide this heat. By the way, one doesn't need a full-up Dyson sphere. You don't need to absorb all the radiation from central star. You could have a ring which only absorbs some relatively small percentage of it. So in particular, these surveys that have been already done for Dyson spheres without people realizing they were doing it were sensitive to fractional infrared luminosities, about 1 part in 1,000. So what that means is, imagine you're standing here on Earth and you look up in the sky and you see the moon. Well, let's say we didn't have one moon, but we had 200 moons, and you filled our sky with 200 moons. That means that if you were in such a situation, looked out into space, 1 time in 1,000, your line of sight would hit one of these moons. And that's the amount of sky coverage that is relevant for the projects that have already been done. They're sensitive to Dyson spheres with a fractional infrared luminosity about 1/10 of 1% of the luminosity of the star about which the putative Dyson sphere is orbiting. So these constructs only have to block about 1/10 of 1% of the light from their central star, would be white dwarf or main sequence star, and they in principle could be detected by current level of technology we have right now on Earth.
So I'd love to sort of synthesize then all of the thinking that you talked about, sort of even just during this episode, and I'm sure the countless other papers that you've worked on. I mean, the Fermi Paradox, I find the Fermi Paradox as troubling a concept now as I'm sure when Fermi first unleashed it on his lunch mates. Where are the aliens, do you think, at this point?
Well, I personally don't think they exist. I mean, I'm definitely in the capital N equals 1 or at most a couple in our galaxy. I think technological life is very rare. I think probably even simple life is rare, but we won't know that until we actually either find life on, or evidence for either extant or fossil life on Mars, or until we launch something like Terrestrial Planet Finder, or the European Darwin, where we can actually search nearby star systems for Earth-like worlds and see whether they're living or not. My guess is when that happens, that we're not gonna find any living worlds. I'm talking about simple life, not technological life, just sort of any life at all.
Yeah.
I just think the origin of life is hard. That's my personal belief. I don't have any. In this paper I wrote some years ago, I think I can present good arguments as to why technological life, it's basically an extension of the Fermi Paradox, is rare in our galaxy. I think in terms of simple life, nobody really knows. It's still a guess. And my personal gut feeling is that even simple life is rare, and it's because the origin of life is not so easy as some people think. But I don't have any better knowledge of insights into this than anybody else. So until we actually do the experiment, we're just not going to know.
Yeah, it's interesting. I mean, I had a chance to talk to a biologist who sort of has been thinking about that side of things, and I talked about, like, what is the difference between simple life and complex life when you have when you have fairly simple life forms coming together in larger and larger communities, performing behaviors that are more similar to complex life, like when you have an ant versus an ant colony, when you have one bacteria versus a bacterial mat. And, in our conversation, he kind of agreed that in fact there probably is no real specific delineation between what is a simple life form and what is a complex life form. And so to make that arbitrary line in the sand and say, well, simple life is everywhere, but complex life is nowhere, isn't even really a fair thing to say. I mean, my audience knows I'm in the exact same camp as you. I'm firmly in the belief, or my suspicion holds, that we are alone in the observable universe, that they would have been here by now. And so I know that you have done a lot of thinking about sort of our role in the environment and what we humans are doing to our own planet. How does that fit in with that possibility that we are alone in the cosmos? What do you think our responsibility is to our planet and to the future of humanity?
Fraser, you've hit upon the second great interest of my life, and that is life here on Earth, and how we're decimating it. It's just so sad. I mean, this could be such a, many people think of, life, well, it's going to be all over the place and everything. It's nothing so special necessarily about Earth life, in the sense there's lots of other life out there, but we don't really know that. And we're just decimating so many other species. I don't think that that we're going to wipe ourselves. Some people think, well, technological life in the universe might be rare because you get to a situation like we're in, and then the creatures destroy themselves through nuclear war or climate change or pandemics or destruction of the oceans, whatever it is, you name it. You can think of a half a dozen different things. As foolish as we are, I don't think that we're going to do that to ourselves. We're going to do it to a lot of other helpless species on Earth. When finally the nadir is reached and we turn things around and we learn how to live sustainably, whoever survives to that point will be living in a biologically very much diminished world. And it's really sad, in my opinion, that that's the way it's going to turn out, but it's just inevitable given our current overpopulation, overconsumption, and with very little desire from the powers that be. The politicians are basically controlling the countries of the world, that this is going to change anytime soon. It's not, unfortunately. Now, I'm going to be gone long before the nadir is reached, but well, I don't envy the people who are going to live into the 22nd century, and some of them are already here. They've already been born and already living.
Well, I sort of think about this, like, if we are alone in the universe, then what a tragedy that we had this opportunity to bring life to the universe, this wonderful special thing, and we sort of either messed it up or delayed when the dolphins could rise up and they could be the ones that actually figure this out, or the squid or whatever. So another sort of concept that you've sort of thought about is this idea of directed panspermia. So let's say that we are alone, that it's just rocks and hydrogen and helium as far as the eye can see, and that the universe is made better with life than without it. What could we do to sort of spread life to the universe?
Well, Brad Hansen, who I mentioned before, one of my colleagues, and one of his students have, and another group now at UCLA, have estimated that something like 30% of the planets, at least planets that are orbiting around solar type stars, have habitable planets in orbit around them. So that just because a planet's habitable doesn't mean that life is going to originate there or exist there, but in principle it might. And so if Brad and these estimates are anywhere near right, then one thing that we could do with directed panspermia is to send life to these other worlds, these habitable worlds, and see whether it might be able to take hold there. That's still, I think, pretty far in the future. Again, we got to get by our own problems here before we're seeding any other worlds with life. But in principle, that's the kind of thing. If we find that there are all these habitable worlds out there, but no evidence that any of them have life, or very few, if any, have life actually on them, and we can learn that by studying their atmospheres and composition of atmospheres and things like that. Then we could try to program directed panspermia. That would be presumably a lot cheaper than actually sending people, in giant space colony. We could this problem of long trips at high velocities would be a lot less severe for carrying out a program of directed panspermia rather than actually trying to settle or colonize these other worlds ourselves.
And what would a directed panspermia look like? How would that, what would you be sending?
I guess you'd send a rocket which try and make a soft landing on the habitable planet, and then just dump a whole bunch of microorganisms there, basically. In this paper I wrote in 1985, I actually had the technological civilizations controlling these rockets, these spacecraft which are carrying all the bugs, with controlling them for most of the trip with giant space telescopes in the home planetary system, and then the actual spacecraft only has to take over at the very last bit of time, just shortly before it actually tries to land on the exoplanet, the habitable planet, and let loose its cargo of microorganisms or whatever else we decide to send.
Yeah. Right. It's interesting that if you sort of synthesize all of the ideas. I know, like, Japanese researchers recently found microbes that had been living under the ocean seafloor for like 100 million years, and they dug it up and fed it, and it was back in business, ready to keep going. That you could wait with your giant interferometer, direct your spacecraft on that short hop when the opportunity approaches, and you just smash a rock filled with bacteria into another planet, and you give life a chance to, and then hope that when they evolve into something interesting, they do the same. They pass it forward.
Yeah, that might take, on Earth, it took quite a while to go from the first microorganisms to complex life. But anyway.
Yeah, but you're saying there's a chance.
I think so. Yeah. I definitely think there's a chance. And in fact, when I used to teach a Life in the Universe course at UCLA, I used to, say some serious what I thought were, try to be serious words about the idea of panspermia and even directed panspermia, because we don't, the great missing step, piece in the march of life on Earth, is how did you go from the primordial soup in one of these warm ponds or something, or the vents at the bottom of the ocean, the hot vents at the bottom of the ocean? How do you go from some mix of chemicals to the first living cell? And we don't really know how that's been done, because there is this mystery. It allows alternatives, such as actually life didn't originate on Earth but came through panspermia or directed panspermia as alternatives. And one might think that's just sweeping the problem under the rug, but there are a number of reasons why it's more than just sweeping the problem under the rug. It may be that life elsewhere originated in some form that's much simpler than the cell, which is so complicated, but we don't know what that form is, because we don't see any of that on Earth. But it might have originated in some other way on some other planet, but then either through panspermia or directed panspermia, the cells actually got sent to Earth. And so the simplest life form on Earth might have been a cell. Whereas somewhere else, which had maybe more favorable conditions, maybe more reducing atmosphere or something like that, on another world, it might have been easier for life to originate in that world, develop cells, and then cells got transported to Earth either by panspermia or directed panspermia. There's also this chirality that it's been a mystery to some people as to why life is chiral, why we have a handedness, why are all creatures left-handed on Earth, left-handed, right-handed, depending on which molecules you're talking about. So that's been a problem that's been batted around by many scientists, and I can think of two explanations for that. One is that life originated only once in the entire history of the Earth, and it happened to be, the chirality we have. The other one just never began. And the other possibility is that it came from panspermia, or directed panspermia, right. And it came in a chiral form, that whoever sent it or ever came here was only one-handedness of cells, and so that would another way to explain chirality. So panspermia has a lot of virtues associated with it, and I don't think it should be ignored.
Mm-hmm, mm-hmm. Yeah, absolutely fascinating. And we've reached the end of our hour. I don't want to take any more of your time. It's been absolutely fascinating, and I really appreciate you taking this conversation into some of these concepts. A lot of they are philosophical, and something that I know a lot of people wonder and think about as we sort of recognize our larger role in the cosmos. We run up against these ideas. So I really appreciate you taking the time to chat with me today. If people want to follow your work, where should they go? You're on Archive, so
right. There is this astronomy archive. It's called AstroPH, yep. Or ARXIV. You can let them know, your audience know maybe how they can access that. And so if you go to that and you plug in my name in particular, and a range of years, you can see what papers I've been involved with. Most of them don't have to do with these topics.
Yeah.
But we've been talking about today. Most of them have to do with much more conventional astronomy, but anyway, they'll be there too.
Terrific. Well, thank you so much for your time. I really appreciate it. I know the audience really enjoyed the conversation as well. And let me know when you do find aliens.
Okay.
Thank you so much.
Bye-bye.